So what I mentioned is that this dynamic debt thing. The idea is that you have this first cheaper network and the second more expensive network, and you have this predictor that uses the features of the first network, and also the features of the first network are used in the second network. And this, so the predictor essentially determines whether the second network should also be run, right?
So the question, so you want to use the first chip network to predict whether the second network should be used, right?
This is right. I think that,
This is iterative. This is also what I do. That on to, I understand that. Yes, I understand the logic.
So as I claim that it works. so there's like the.
Can you also use the first one using a random forest? Instead of using what's the purpose of using a neural network first? Because you can reuse some results.
Well, I mean, yeah. So if this thing says no, then you just use the result from the first one, right?
Yes.
And this is like computer vision. It's for detection.
Okay.
So
you already do some classification.
yeah, I mean they already detect object, right? So this one detects objects. It's worth it, right? Because essentially the argument is that some images are like easy and some are hard, right? So that's kind of the idea that. Idea is that you have some images, easy images, some hard images, and then you run the first detector. And features tell you that you should use the second one, and then you do that. But otherwise, you use the first one, right? That's kind of. And to me, that seems like this could be used as part of an ensemble learning.
Well, it's different. In ensemble learning, we like to not only use two, right? We would use quite more.
Yeah, but I think you could, in theory, do this with more, right?
No, in theory, what you do is that you want to. So every model has its own strengths. In the ensemble learning, it tries to demonstrate that you can utilize as much strengths as possible. Yeah. So you get the pollution from the bad model, but you have to say that this pollution is not going to kill me.
All right.
So it's therefore you need to have a lot of them. So and you hope that for each of them they are. If you give me a bad result, the others will give me a good result. So your impact will be gone. So this is the art of ensembles, not just to look at the individuals. So you look at the global. It's like that if a majority would give the good prediction of everything, then you can take the majority of everything, right? So even if you could bring some results for that specific input, the others will compensate your wrong result. And that is the art of ensemble. Otherwise, we just arbitrarily use anything, right? So if the ensemble model has the concept. So I have a lot of random forest, decision trees, and some we can assume that majority would be good for most inputs, then the ensemble will give me the nice results. But I cannot say that this decision tree has a more important factor than the other. I mean, yes, for the input. But you hope that.
All right. So one other thing, maybe, what would the professor on Monday mentioned? It's like, at least it seems to me that it might be an interesting idea to have, if you have like an ensemble learning thing, that you merge them, right? If you can.
But this is ensemble model is different in the concept. You just think about what I say. It's actually it's different from resource perspective, right? So
wait, what do you mean?
Usually, in ensembles, you need to have, let's say, for random forest to work, you need a lot of trees. So that you can say that majority will work. This majority works. Now, if you start to reduce the number of trees, then this concept of majority works is gone, right?
Yes.
They start to have some defects of some regions, and then it may become a big problem later on.
Yeah. Well, I mean, for example, I think the one example you gave was like 8 ResNets, right? where they then merged and maybe pruned. I'm not sure. I think it's so.
Ja. Hallo, guten Tag. Wir kommen zur Vorlesung Rechnerstrukturen. Gibt es noch Fragen über Floating Points Addition? Keine? Ja? Oder Subtraction?
Also, wenn ich das richtig verstehe, die Subtraktion von Fließkommazahlen, also wenn wir möchten subtrahieren, dann also müssen wir zuerst also Mantisse gleich, ich meine Exponenten gleich machen und danach Zweierkomplement, Mantisse in Zweierkomplement darstellen und dann addieren. Genau, und dann normalisieren.
Zuerst Sie bekommen zwei Zahlen, x und y. Wir gucken, welche Zahl hat eine große Absolutzahl. So, dann dieses ist unser x und dann das ist unser y. Wenn die zwei hatten verschiedene Exponenten, normalerweise in unserer Übung nicht gleich, natürlich, dann muss man ein bisschen die Mantisse verkleinern. Ja, das ist für unser Ding, das ist my ist zu groß. Wir müssen ein paar Stellen nach rechts schicken. So, wenn es ist für Addition, dann man schickt einfach mit Nunnen vorne. Wenn es ist Subtraktion, dann es gibt zwei Möglichkeiten. Zuerst schicken nach rechts, dann haben Sie zuerst Nunnen vom Anfang. Und dann, das ist my mal 2 hoch ay minus ax. Okay, das ist richtig. Aber das ist eine Subtraktion. Da müssen wir mit Zweierkomplementdarstellung umwenden. Ja? So, dass man so. Mit Zweierkomplementdarstellung, dann bekommen Sie die richtig Binärzahlen zu addieren. Dann das ist eine Subtraktion. Ja? Okay? Das ist richtig. Ja.
Ja, okay.
So, Subtraktion ist ein bisschen schwieriger. Aber das ist gleich wie Addition. Okay? Alles verstanden? Das ist so, Addition ist einfach. Addition ist auch einfacher. So, wenn wir über Multiplikation gucken, das ist ein bisschen schwierig und einfacher. Okay? So, welcher ist schwieriger? Jetzt machen wir mx mal my und ax 2 hoch ax mal 2 hoch ay. Ja? So, wenn wir die zwei Zahlen haben, x und y, und dann das ist 2. Wenn wir x mal y möchten, das ist jetzt minus 1 sx mal minus 1 xy. Okay? Dann mal mx mal my mal 2 hoch ax plus ay. Ja? Das ist einfach Multiplikation von zwei Zahlen. Okay, dann müssen wir genau gucken. Das ist unser z, sz. Und die zwei zusammen ist unser mz. Und ax plus ay ist unser az. Ja, das kann man einfach so verstehen. Ja? So, dann, was ist sz? So Sx ist entweder nur oder 1 und Sy ist auch entweder nur oder 1. Ja? Dann gucken wir jetzt hier. So Sx, warte mal, Sx, Sy. So wenn beide nur sind, so beide Zahlen sind positiv. So Sz ist auch nur. So Sx ist 1, das bedeutet, Entschuldigung, Sy ist 1, Sx ist nur, dann x ist positiv, y ist negativ, eine positive Zahl mal eine negative Zahl ist negativ. So, Sz ist 1. So, Sx ist 1, Sy ist nur, x ist negative, y ist positiv, so, das ist auch 1. Wenn beide Sx und Sy 1 sind, dann Sz ist auch nur. Okay? So, die Frage ist, was ist Sz? So, nehme ich immer an, dass wir die zwei Zahlen nicht besondere Zahlen. Ne? So, nicht plus Infinity, nicht minus Infinity, aber zwei Zahlen, die wir darstellen können. Okay, so gucken wir noch einmal. So, natürlich, das ist einfach, wenn wir noch über Tabellen gucken. Es gibt die zwei Dinge. So, Sz ist nicht Xx, Sy oder Sx nicht Sy. Ja, das haben wir schon früher geguckt. Und das ist bei Definition eine nicht Ort, nicht End, nicht Nennt. So, das ist exklusiv auch. Ja? Gut, sehr gut. Okay, gucken wir noch einmal. Zweite Frage. So. Bin unsicher, was diese Frage ist. Okay, keine Ahnung. Das ist zu fern. Wir gucken mal später. Ja, das geht. Schon hier. Das ist dieser, nicht die zwei. Okay, gut. Dann mx mal my. Und ax mal ay plus ay. Für die zwei müssen wir noch gucken. So, das ist ein bisschen kompliziert, weil die Exponenten mit Exzess dargestellt werden. So, wenn wir jetzt die zwei Exponenten gucken, ax plus ay, so zum Beispiel ax ist 1 und ay ist auch 1, das ist ax plus ay ist 2. Aber in unserer Exzessdarstellung, die Darstellung ax ist 128 und ay ist auch 128. Ja? So deswegen müssen wir genau gucken, welche Operation wir dort brauchen. Ja? Es bedeutet, wenn wir über die zwei Darstellungen ausnehmen, müssen wir zum ersten eine von die zwei minus Bias berechnen Und danach können wir die zwei addieren. Okay? So, was das bedeutet, habe ich diese Fragen. Any question?
Yeah, I mean, just what was written there seems readable, doesn't it?
What?
I mean, what, on the slides, right?
On the slides?
Yes.
It's wrong or not
I mean,
wrong?
I think the right thing is meant, but it looks weird, right?
It looks weird. Why not?
Did you add the bias on?
Yes, that's right. Yes. Let me try to explain. He's confused. Let me see whether I'm confused as well or you are confused as well. Okay, so diese große A ist unsere Darstellung in natürliche Zahlen. Ja? So, wenn ich genau gucken, ist so. So, wenn so Ax, so gucken wir, Ax ist 1. Okay? Dann unser Bias ist 127. Das bedeutet, dieser Ax ist 128 und die Binärkodierung ist 1 nur. Ja? Okay, dann erkläre ich noch einmal. Dann wenn wir über y gucken, y ist zum Beispiel auch 1. Dann y ist auch 128 und das ist gleich wie ein nur 2. Unser Ziel ist ax plus ay. So, dann jetzt kennen wir ax plus ay. So, das ist 2, ja? Das ist klar? Aber wie berechnen wir diese Ausgabe? So, das ist az. Dann brauchen wir az, große az in Binärdarstellung. So, az, große az ist einfach ax plus ay minus b. Ja? So, deswegen, wenn wir die zwei x plus y zusammen addieren, so ax ist 1, ay ist 1, dann die Darstellung, die wir hier brauchen, ist 1 nur 1. Binär 2.
Yeah, but I mean, it says for ex, it says to add the bias, and for ey, it says to subtract the bias.
It says to add the bias. Both add the bias.
No, wait. Here's a. Wait, okay. No, it looks like my minus on my side.
Okay, the broadcast says minus, but it's plus.
Wait, I think it's just.
It's a resolution problem on your computer. Okay, that's the reason why you were confused. Any question? Okay? Das geht? So, es scheint ein bisschen komisch aus, aber das kommt einfach von unserer Darstellung. Unsere Darstellung hier ist mit Exzessdarstellung und die Exzessdarstellung haben wir einen Bias. Wenn wir die zwei Exponenten zusammen addieren, dann haben wir zweimal Bias. Müssen wir eine ausnehmen. Ja? So, dann machen wir zuerst eine Subtraktion und dann eine Addition. Danach können wir addieren. Okay? Gut. So, any question for EZ? Keiner? Dann mx mal my. So, mx mal my. Jetzt müssen wir auch genau gucken, welche Möglichkeiten es gibt. So, mx ist noch einmal zwischen 1 und 2. My ist auch zwischen 1 und 2. Deswegen mz ist mx mal my und mz ist zwischen 1 und 4. Deswegen müssen wir gucken, ob wir normalisieren sollten.
I think when mx and my is exclusive to...
Ah, sorry, that
the-
right-hand side should be less than 4.
Yeah, okay.
Okay, thank you. Yeah. Thanks. Good eye. So that means that if mz is between 1 and 2, you don't need to do anything. But if it's more than 2, you need to normalize that. Okay? Good. Any question? If not, then we are done for this multiplication. Is the multiplication much easier? Any question about multiplication? No? So let's look at one example. So, wir haben die zwei Zahlen, x und y. Dann gucken wir zum ersten sz. sz ist exclusive von sx und sy. Beide sind 1, dann sz ist nur. Exponent. Der Exponent sz müssen wir jetzt gucken. Das scheint ein bisschen kompliziert aus hier zu rechnen, aber das ist ganz einfach. Okay, so wie schon gesagt, iz ist großer iz. Die Binärdarstellung mit Exzessdarstellung ist ax plus ay minus b. So, hier ist unser ax, hier ist unser ay und dann müssen wir minus b machen. Minus b ist 127. 127 ist 128 minus 1. Ja, so, es ist ein bisschen kompliziert dort zu machen mit vielen 1. Dann machen wir einfach die zwei. So, ay minus b. So, hier ist ay. Hier ist 128. Hier ist minus 1. Okay, dann, I know that we don't do minus, as I always say, but when we cheat, we can do it. So, dann, das ist einfach, so dann können wir diese 1 ausnehmen und dann, das ist plus 1, ja, so das ist einfach 8. Okay, 7 plus 1 ist 8. Okay? So, das bedeutet, unser Kleid ay ist 8. Dann, wrong?
The next is wrong.
Which one is wrong?
It's twice or something.
Which one is twice? Which one is wrong? Let's see.
It just said it twice for one.
Ah, okay. Yes. Yeah, okay. So you don't see this, right? Doesn't exist. Yeah, good. So, sorry, we made a new slide. So the only way to make the slides correct is to teach. And because when you look at that, you never know it. Only until a moment and you need to go through the equation. So if you find something wrong, it's wrong. Tom is your TA. Ja. Okay, gut, dann machen wir jetzt ax plus kleiner ay, das ist großer ax plus großer ay minus b. Und dann können wir jetzt addieren. Die zwei, so 1 nur, 1 nur 1, plus nur, 1 nur, das ist 1 nur, 1 nur 1. Okay, das ist unser Exponent. Schaut gut aus. Okay. mz, das müssen wir auch gucken. So, mx ist 1, 1 nur 1. My ist 1, 1, nur 1. Okay. Dann müssen wir die zwei zusammen multiplizieren und das ist by definition 1.5. more than 5, one is more than 1.5, another is more than 1.5, dann ist es größer als 2, müssen wir dort noch später normalisieren. Ja? So, das geht zunächst. So, 1,1 nur 1 mal 1,11 nur 1. Das Ergebnis ist 1 nur, 1111 nur 1. Okay? Das ist größer als 2. Okay? Wenn dieser weil dieser größer als 2 ist, müssen wir normalisieren. So, der Exponent müssen wir um eine Stelle vergrößern und wir müssen die Mantissa nach links nochmal schicken. So, das bedeutet, unser Mantissa MZ ist 1, nur 1, 1, 1, 1, nur 1. Wenn wir dann am Ende codieren, nennen wir nur die Nachkommateile. So, deswegen, dieser ist unser Mantissa und der Exponent ist dieser plus 1, das ist 1 nur, 1, 1, 1 nur. Das sehen wir einfach hier. Okay? Gibt es Fragen? So, ich erkenne noch einmal. Die Addition und Subtraktion und die Addition, Subtraktion und Multiplikation von Gleichkommazahlen sind fast gleich. Für Addition und Subtraktion müssen wir in großen Bereich von Exponenten bearbeiten. So machen wir zuerst dort. Wir suchen die große Zahl, die wir verarbeiten sollten. Und dann bekommen wir die MZ. Und wenn diese MZ größer als 2 ist, müssen wir normalisieren. Okay? Für Multiplikation, das ist fast gleich, machen wir zuerst. Wir können zuerst diese MZ berechnen. Diese MZ ist mx mal my. Es gibt Möglichkeiten, mx mal my größer als 2 ist. Wenn mz größer als 2 ist, müssen wir auch normalisieren. Wir müssen die Exponent an einer Stelle erhöhen und dann mz durch 2 machen. Durch 2 bedeutet, dass wir an einer Stelle nach rechts schicken. Auch Komma nach links schicken. Und am Ende müssen wir immer das explizit 1 wegwerfen vom Mantissa. Any question?
Also ich habe eine Frage, also wie dividieren wir? Division.
Division, machen wir Division von Fließkommazahlen oder?
Ja, von Fließkommazahlen.
Wir machen hier gar nichts. In this whole lecture, we don't do division. Okay. The only division you did is algorithm 1 in the first lecture, and we never do it again. We would never do that. I would not try to do that either, to confuse you.
Okay.
Yeah. It's much more complicated in a way. Okay, any question?
Maybe we should note that for the exponents, the order for the addition matters, so that they don't add the exponents and then do the overflow.
Just tell them.
Wenn man die Exponenten addiert und den Bias abzieht, ist wichtig, dass die Ordnung ist wichtig, ja, also weil wenn wir Binärzahlen mit begrenzter Bitkapazität halt immer haben, ist das Ganze nicht kommutativ, ja, also weil es halt zum Overflow kommen kann. Nur so als kleiner Hinweis.
Okay. Okay, now we need to do something. I would have to stop sharing my screen because of the copyright issues. Can you just make sure that we don't share this? Yes, thank you. So we are not playing anything, but we can have a look of what, oops. Can I make it full screen? But yes. Okay, this is Ariane 5. So Ariane 5 is a success of Ariane 4. Ariane 4 was a success of Ariane 3, of course. Designed by European Space Agency. The launch was in 1996. It cost quite some money at that time. Okay. Before this Ariane 5, everything worked well. Okay, and Ariane 5 had the launch in June of 1996. A few seconds after, you will see that. Usually I would stop here, but I think it's better to let it continue. Okay. So what happened was that they tried to convert a 64-bit floating point into 16-bit floating point. Oh, sorry, 16-bit integers. So basically, when it has an overflow of the integers, it goes to negative, and everything goes to something that doesn't exist. Yeah. So they tried to solve a problem that did not exist at that time. Okay. So floating-point errors. In 1991, the Patriot missile accident happened in Iraq. So the idea was that when you want to, I think now we all know the anti-missile systems. So when you want to intercept a missile, you will need to calculate the trajectory. The question is how you calculate trajectory. Now you can say that you calculate trajectory in a scale of 100 milliseconds, and then you calculate how much time the missile has traveled, and then you calculate where to intercept with the missile, right? The question is whether you have 100 milliseconds. You can think about 100 milliseconds, but when you program that as 0.1 second. And the problem is that you don't have 0.1. You have something that is greater than 0.1 or smaller than 0.1, and you say, well, it's a minor problem, right? It's not 0.1, but 0.099999. Now, if you accumulate for the error with the error for a long time, a few centimeters will be enough for you to make the mistake. Okay? So what's the difference here? If you do 100 milliseconds, it's 100. It's an integer. If you do 0.1 second, it's 0.1. It's a floating point that you cannot do it at all. So it doesn't work. Okay. Then you ask me for 14 points for division. There's a division circuit. Because it was complicated and expensive, Intel decided to use a lookup table. And the lookup table was wrong. It cost Intel a lot of money to call it back. So that's one of the scandals in Intel's history to recall those bugs. I talk that in English because it's not part of the exam. All right, so I'm going to continue with that. What I'm going to say next is not part of the exam. But I hope you will remember what I said today. And then keep in mind that you don't use 14-point numbers until the moment that you know what you're doing. Okay? So don't use 14-point numbers unless you know all the defects of 14-point numbers for serious business. So if you want to design some program that may involve human lives, or they may involve a lot of money for constructing a machine or spacecraft like that, use the 14 points with extreme care. And you need to know what are the possible consequences of 14-point numbers.
Als ganz kurze Addition, also insbesondere ist es auch so, dass es gibt andere Möglichkeiten. Also wenn ihr Floating-Point-Zahlen sind dann gut, wenn ihr nicht absolute Präzision braucht. Ja? Also wenn ihr in einer Bank arbeitet zum Beispiel, solltet ihr nicht Floating-Point-Zahlen dafür verwenden. Ja?
Ja.
Sondern es gibt eben spezielle Bibliotheken zum Beispiel, die halt Arbitrary Precision erlauben ohne Floating-Point-Rundungen. Ja? Also ich weiß gar nicht, ich glaube Big Decimal heißt es in Java oder sowas. Einfach mal suchen.
So what I'm going to do next is computing in English. The slides are in German. I just converted that today. So, I'm sorry, not the German part, but the Decker part. So you can download that from the website. First of all, this is not a lecture about numerical analysis, but this is a lecture you first touch the nice idea of binary representations, 14-point numbers. When you talk with the others, they will tell you that, well, if we don't know which number we are using, let's declare it as a float or double. If we are not sure, let's declare it as double-double. And then you think that these are real numbers, or they think these are real numbers, and you tell them, no, these are not real numbers. We only have 128 bits. We cannot encode more than 2 to the power of 128 values. So they cannot be real. They must be discretized. It looks like they are real, but it's not real. It's an illusion that's real. If that would be the only case, then we don't need to talk about the defects of 14 points, right? We have to think about what we actually face. First of all, when you use computers to do calculation, we already know that with the integers, we have to pay attention to overflows, right? Now, what do we have to pay attention in terms of 14 points? We have to pay attention to its imperfectness due to the design policy of 14 points. With the integers, it's easier that you say that if I add two positive numbers, it could become negative, so I have to pay attention whether it flips the sign. Adding two negative numbers could become positive, but I can still do some mechanism to check that. Yeah? So how about floating points? I add two numbers. They seem to be correct, but mathematically 0.1 plus 0.2 will be 0.3. That's correct, right? If you put that to your program, checking whether 0.1 plus 0.2 is equal to 0.3, it will tell you, sorry, it's not correct. You can say, oh, what's going on? Is our mathematical rule going to break, or what's going on here? Well, now you should keep in mind that this is a feature of 14 points. 0.1 plus 0.2 is not equal to 0.3. Mathematically, they are the same, but under the 14-point representation, they are different. Okay? Can you tell me why they are different? What's the reason that they are different? Now you learn how to add two numbers, right? What's the potential reason that they are different?
I simply think that due to the mentioned flaw of floating point numbers, since that's 0,1, it's actually 0,9999, then plus 0,2, then it's 0,29999. So it's not actually 0,3.
But now it's correct, but why? In the other one, it's 0.1 plus 0.3, that's equal to 0.4. If your explanation is correct, then we should get both of them with false, right? But one of them is correct, another is not.
Then probably 0,2 is the one which is 0,1999.
That's, I don't want to look into the numbers, but what's the reason? Now you learn how to add two floating points. So what would be the main reason that you could have such difficulty? When we add two numbers, we first check which number has a larger exponent, right? And when we try to add mx plus my multiplied with 2 to the power ey minus ex, if ey minus ex is negative, we need to shift. When we shift, we may lose something. When you lose something, it may be different from what you intended to do at the beginning.
Because you only have 32 bits.
You have 23 bits for the mantissa. You shift one to the right, you lost that last one. The last one is potentially the one that you need to get this right? Then it's gone. Okay? So that's what he said. When you look at 14 points, you would say that nothing is exact. No, everything is exact with its representation. But the question is that whether you would lose something important or not. Okay? So this is the nice part of 14 points. And also, the nice part of 14 points is that you can have a lot of accuracies. You have a lot of values in the range, but you start to lose something. Okay. So keep in mind that if you write your program like this, it would be a terrible thing to do. So what you should not do in your program when you do 14 point is that you declare a variable as a 14 point. You say that if that variable is equal to 0.1, then I do something. Otherwise, I do something else. The problem is that you are not sure whether you exactly get these two numbers right. It's not 0.1, it's 0.999, it's 0.099999 something, or 0.1000001. The question is, which one do you want? Now, so in a standard, there are ways to define how you round up and round down for the last bit in the mantissa. But it's at the end, when you write a program, you have to be very sure about your behavior. Using 14-point numbers as a flag in your program is a terrible idea. Okay. So such checks should not happen when you use 14-point numbers. Okay, better not do that. Instead of using 0.1 plus 0.2 equals to 3 or not, 0.3 or not, you should scale your system. Let's change the system to integers with a unit of 0.1. So I can check whether 1 plus 2 is equal to 3 or not. It will work correctly. Okay, so now if you do rounding, you get the same thing, right? So essentially what you can say is that 14-point numbers are like piles of sand. Every time you move them around, you lose a little and then pick up a little dirt. So you get something that is a pollution, so try not to use that unless you know what you're doing. Okay, good. Next question. So 14 points. So I had this question earlier. Now it's time to ask you this again. I have A plus B. Okay. So minus C. And I can do also B minus C with 9 plus A. Are they always the same? Not really, right? Because now it depends on whether you get something from A plus B or you lose something from B minus C. Okay, let's try to do one thing. So if A is not 0, B is not 0, and A is greater than B, is it possible that A plus B is equal to A? Is this possible or not? A is greater than 0, B also greater than 0, but I put A plus B together, and the result says that this is equal to A. How is this possible? Can you give me an example that this is possible? I think you know the answer. So do you want to try to tell the others? Maybe. You already almost got that.
No, thank you.
No? Yes.
Maybe as soon as you lose bits.
A bit is probably not enough. You need probably lost a lot,
okay,
right?
Okay.
So let's think about that. Let's say A is...
Maybe if those two numbers, A and B, are so far apart in the exponent that it can't really represent the whole
How far do you need? How far do you need? You say so far, but how far do you need? It's not necessarily too far. He gave you an answer earlier already. He said something earlier, and that is the exponent difference you need.
Yeah, maybe when the difference is greater than 32, or the
2 to power
amount
32?
of bits you have
In where?
in the mantissa.
23 bits.
Yeah, for example, with the format.
So we can try to do that. We can add these two numbers and see what happens. So add A is 2 to power 23, and B is 0.5. Okay, so let's say we take these two. So A is 2 to power 23, B is 2 to power minus 1. Okay, now you know the exercise. Let's do this. X is A, Y is B, EX is 2 to power, EX is 23. Right, now we have to do the mantissa. MX is 1, MY is also 1. But EY minus EX is minus 24. So I have to shift MY towards right with 24 positions. It becomes 0. It's gone. It's just gone. It doesn't exist. Originally, it was 1. By shifting that with 24 positions towards right, it becomes nothing. It's gone. So it becomes 0. So when you say that, you check A is not 0, B is not 0, you do A plus B, the output says that it's still A. It's a feature first. It's a feature. It's just like whether you know that this feature is going to become a problem or not. Let's look at a case. This feature actually becomes a serious issue for our analysis. So, numerical analysis 101. You have two numbers. You need to put them in a division. F of x is 1 minus cosine of x divided by x to the power 2. Of course, the question is that when x is close to 0, then you can say, well, 1 minus cosine 0 is 0. X to the power 2, when x is 0, it's 0. Something divided by 0, undefined. Okay, this is not a question I want to ask you. If x is 0, it's another story. Let's say that x is not 0, but close enough to 0. Not 0 first. What do you get here? Mathematically, you don't know Taylor expansions yet. So I could try to explain this using calculus. So does anyone here know anything about calculus? You learned that in high school or not? I think your high school is a little bit close to my high school time. Analysis, yeah. So can someone explain me the L'Hopital's rule? 5. Okay. Again, this is not part of the exam. This is not a lecture of mathematics, but this is the thing you will learn at some point in time in the university, or you learned it before. Or you will learn another way to do this. You can use Taylor expansion that you will learn in the next semester, and the result will be the same. Okay. So the fact is that this is 0.5.
Ich weiß, dass wir nicht x gleich 0 setzen dürfen, weil sonst haben wir eine 0, sonst teilen wir durch
It's
eine
a
0.
Limit.
Ja, ich weiß. Aber müssten wir dann nicht x gegen 1 laufen lassen, damit wir 2 mal x gleich 2 ist?
Ich verstehe nicht.
So we can't make the x 0 because we can't divide through with a 0.
Yeah, the question is that when s is close to 0,
yes.
what is this? Yeah.
But isn't it close to 1 then, if we want to do 2 times x equals 2? So because if we go closer to 0 and but further than a 1, the 2 gets smaller, or are we only doing
You do this
whole numbers?
when x approaching 0, and according to this definition, it's still 0.5.
So only with whole numbers? No decimals?
No, all numbers.
Okay.
All
Yeah,
numbers, yes. Okay. Okay, good. But as I said, this is just the fact that this is 0.5 by mathematics. If you go to a lecture of mathematics, they will tell you to solve it, it will be 0.5. Okay. What do you get from computers? Of course, it's different. Otherwise, why are you talking? What's going to happen if you put that to your computer? Is it going to give us 0.5 or not 0.5? It should be something different. Otherwise, I'm not going to talk about that here. So how does that look like? Oh, it looks a bit arbitrary. It goes up, down. It even goes to something closer to 0, and well, you get lost. Okay, what went wrong? What was wrong there? What happened there? Any idea? Any idea what's going on here? Okay, so if you understand Taylor expansion a bit, 1 minus cosine of x, when x is very close to 0, using Taylor expansion, is actually x divided by 2. Approximately, not exactly, approximately x divided by 2. And why is that the case? Do the Taylor expansion. X to the power 2 divided by 2. Yeah? So it's in fact x to the power 2 divided by 2. And x is very small. And then x to the power 2 divided by 2, and then divided by x to the power 2, it's actually 0.5. That's how the mathematics works if you do first Taylor expansion. Now, since we don't do Taylor expansion, we first do 1 minus cosine of x. Okay, good. So now the problem is that 1 minus cosine of x, when cosine of x is very close to 1, but not 1, how much do we lose? So we lose quite a lot, because coming back to our example earlier, a plus b. Now let's do it a minus b. A is very close to 1. Oh, sorry, A is 1, and B is very, very close to 1. So A minus B. Now the question is that when you have A and B so close to each other, the non-significant part of your mantissa is what you want to have in a representation for cosine x. Right? Because everything would be cancelled out, all the ones would be gone. The mantissa 1 minus 0, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. At the end, the later part of those ones would be your accuracy. The less you have there, the more problem you have. Okay. So similarly, on the other side, when we look at x to the power 2, when x is so small, the x to the power 2 would still keep some position of a layer. So what you get is that when x becomes small, your value jumps up and down, so depending on where you are. So what happens is that one. This cosine of x, when you put x closer to this value in, it's precise up to here and still have some values here, right? And then you do 1 minus cosine of x. This is what you get. And now the later part, x to the power 2, will not be able to have this accuracy as well. So you get a problem that depending on where you are, you get up and down, but it's not 0.5, depending on which accuracy you lose over there. So what happens here is that when you look at this idea, you originally thought that A minus B, if you want them to be 0, they should be close enough to 0. The least significant part matters. Okay? But due to that inaccurate format of floating points, you don't have that part being represented precisely. You got in your mantissa no sufficient representations of the accuracy. It could happen in a 1 minus cosine of x. It could happen in x to the power 2. But in this case, this is due to the so-called catastrophic cancellation. You look at this 1 minus cosine of x, and this 1 minus cosine of x is not precisely represented. And this cancellation gives you the problem to handle the accuracy. Okay? Any question for this so far? So when you take the floating points for cancellation, the question is that, is this cancellation going to always work? Or you will have some catastrophe at the end?
So if I understand it correctly, the reason for that is because it's really similar to that first one when two numbers are very far apart. But here it's the reason because they are really close, but we actually represent them in Zweier complement. And because of that, they actually become very far apart again, and again we have the same problem.
They are not far apart, but they are not precise enough because of the loss of the mantissa bits you have. Because you basically cancel all the important parts. The original important information becomes a troublemaker. The least significant bits are the bits you need to have the precise calculation over here. Okay? Okay. By the way, if you see different results from this one, let me know. That computer must be implemented incorrectly. This is a correct result in computers. This one is correct from computer's perspective, but incorrect from mathematics perspective. Okay, so there have been many results. You see, we already did that. What I'm going to tell you as the last one is that you may think that, well, is that really a problem? Yes and no. Let's look at this well-known problem. You learned this also in high school. but with a different name. Do you know? Daniel, do you remember your high school life? What is this called?
Linear control. What do you mean? Linear testing?
The same thing? It's called, the method is called Gaussian elimination.
Yeah, so, yeah. It's also.
What was that called in high school? See, I'm not very sure what I learned in the past, but maybe you remember.
Das solltet ihr auch alle kennen, ja? Also das ist,
Okay.
wie man irgendwas mit Methode von Gauss, ja? Ich weiß nicht, ob man sie so schon damit sie auch kennt, nennt, aber.
All right. Well, let's say we have 3 variables, x, y, and z, and we have 3 equalities. The first one says that a1x plus b1y plus c1z is d1, and so on and so forth. You can write that down as a matrix form, and what you want to say is to find out the variable assignment such that it's left the 3 equations hold. This is basically everywhere. So this is one of the problems that you learn in the high school, and you will still use that.
Gauss-Verfahren, ja? Gauss-Algorithmus.
Okay, so when I was, by the way, when I joined the escape game here at TU Dortmund 2 weeks ago, one of the questions was to solve the Gaussian elimination problem. Okay, good. So now I change that to x0, x1, and x2. So I have 3 equalities, and what I want to do now is that basically what I have to do is to somehow slowly cancel each of them. First, I cancel this a1, make it to 0, make this to 0, and then second, I make this to 0. As long as I can make them to this to 0, I can slowly solve first set is d3 divided by c3, and then based on this value of z, I can calculate y. Based on the value of y and z, I can calculate x. Right? So basically what you need to do is to do the triangle elimination and get the upper triangles matrix. So if I have this value, I can get that x2 is 2, and then x1 is 4 minus 2, so it's also 2, and then x0 is 1. How does that work? You can write a program. The program looks like as follows. As long as you look at you have the triangle matrix, the upper triangle matrix that you have here. You start from the last variable. The last variable is this value divided by the coefficient of the last variable. And then I can fetch this variable into these 2 equations, right? And then continue this process in a repetitive manner. You can easily write a program over here. This is how the program looks like. Okay, good. Now, think about that. You do it in a floating point. What could happen? What could happen is that you may have a possibility that when you construct the triangle matrix, yes, I think here's an answer.
In Englisch?
Up to you.
Erstmal, man hat ja eine Division, das heißt, sobald a, i, j beispielsweise dann 0 ist oder generell das ganze Gleichungssystem keine Lösung hat, kommt ein Fehler. Also
Let's assume we have a solution.
Okay. Und ansonsten es können wieder signifikante Bits verloren gehen, weil man erstmal wieder multipliziert und dann bei der Summe wieder subtrahiert und dann wieder dividiert, deswegen.
Now, the nice problem you will get is that your 0 is not 0. It's close to 0, but not 0. And you will slowly get into trouble of this. Now, we learned that there's no 0 in our system unless we force that. Now, how do you actually get this done in the Gaussian elimination? You first find out how you somehow add one equation to the next equation by multiplying with a constant, right? You multiply with a constant so that you can cancel one of the coefficients out. And this cancellation in your first imagination is that let's find out which number I need to multiply with and then put that in for cancellation. This cancellation in your first imagination is 0, but in the real system, in computers, it's not 0. It's close to 0, but not 0. And it's not 0 leads to the problem he mentioned earlier. Then later on, you classify that as non-zero and divide it with that value, it becomes not a number. So you get a whole catastrophe that you get in this algorithm. This algorithm will never work if you use that for real numbers. So what we do in this Gaussian elimination, you first create a triangle, right? And then what you do is that you first, we have these 3 equations. We can somehow change them to this one. So now we know that these are zeros, so now we have this one. So we can somehow take the second equation, multiply with 3, and then put that as a minus, and this 3 times x2, sorry, x1. What's going on here? Daniel, can you help me give a note that this is x1, this is x1, this is also x1, this is also x1, this is also x1. Okay? So it should be indexed accordingly. Huh? So this is not the fault of our plotting. It was there for many years. Because I never seriously talk about the slides, so please. Okay, so you do this elimination, you write an algorithm like this, and what happens is that you somehow think that this is a 0, but it may end up with something that is not 0. Okay, so this is the process we said earlier, and when you look at that, it's possible that when you swap that, it becomes non-zero, and you have a problem that you have something divided by 0, it's not a number, or it's very small, and then you get a significant inflation of your number over here. So it doesn't work. If you do this piloting of Gaussian elimination in computer systems, you would have tons of problems on that. And you also cannot say, well, if it's 0, let's not do it. You say, by the way, it's not 0, it's just close to 0. We already done it. Huh? You say it's very difficult to get a 0. You can try that. Looking at 14-point numbers, having the exact calculation of A multiplied with B divided by C equals to 0, it's not that easy to always be possible. You first have to find B, right? B is A divided by C, as you want to do. But then, by getting that value, multiplied with A divided by C, it's not 0. Again, 14-point number magic. You always get the problems there. Okay, so if that would be the case, we are in a big trouble in computer systems to do any linear equality. Right? So you would have a problem to do Gaussian elimination over here. So the idea to do this right is that you have to do it in a better way. You have to somehow do this so-called partial pivoting. The partial pivoting says that you always take the maxima absolute value as the element you want to eliminate. So you make sure is that your cancellation is not the most catastrophic one. If you have some pivoting that's close to 0, you would put that to the lower ones, but not put them at the beginning. With this pivoting, partial pivoting, you get the better solution of that. So what's happening here is actually that what we are interested in utilizing those 14 points is that we need to create algorithms such that the 14-point representation is not going to give us a big trouble if we increase the number a little bit. So what it says is that we want to prove that an algorithm F to actually FL to calculate F is somehow close enough if we just add the value a little bit. It means that your problem should still be well represented in the floating points if you have some deviation over here. So, for example, if you use you calculate this function, and you calculate this using the number we just put, it's not stable, because when you add a little bit, it actually deviates from the stable points out. So the numerical stable solution is actually a Taylor expansion. You first do a Taylor expansion of 1 minus cosine of x, which is give you 2 times sine to power 2 divided by x divided by 2. And then you can do that with numerical answers of this function. It's all similar if you do this with a Gaussian elimination process. If you don't do anything to calculate this value, there's something close to 0. This 10 to power minus 17 is actually close enough to 2 to power minus 24. We see that number, a plus b, so it's equal to a, right? So look at the a, the value of a is very close to something that is not significant. And now if you start this Gaussian elimination by following the same equation, you will get the result that x is 0 and x1 is 1. If you do partial pivoting that I shortly explained, you will get a result that x0 is 1 and x1 is 1. The exact solution is close to partial pivoting, but not exactly partial pivoting, because you are not able to calculate this correctly for a reason that a is too small. The only hope you get is not to make serious mistakes. What serious mistake you will make is that you will get this non-pivoting. That what happens is that you first multiply with the first equation to 10 to power minus 7. So let's do the calculation here and see what happens if you don't do anything. So let's first do this multiply with 10 to power minus 17, and then subtract to the next one. So then you get this 2 will be cancelled, so we get the second equation would be 2 minus 10 to power 17 times x1 is 3 minus 10 to power minus 3 minus 10 to power 17. Yeah? Is that clear to everyone? So you take this part, you take this part, multiply with 10 to power 17, and then minus, put that equation to the next equation, and then take the minus of it. All right, so then this 1 will be cancelled, and the second one would have this part, and the last one would have this part. Okay? Now we do the calculation. Let's flip the 10. 10 to power 17 minus 2 is 10 to power 17. We know that earlier, right? According to the example we had earlier. One is too big, another is too small. When you take the minus, a minus b is a. The same thing for 10 to power 17 minus 3. So now you get is that you have 10 to power 17 times x1 is equal to 10 to power 17. So x1 is 1. Okay? Sounds weird, right? Now, because x1 is 1, you get x0 would be 0. Finished. Is that clear or not clear? Let me do it again. Or let's do it in other way. So if you don't do anything, you follow the Gaussian elimination process. So this is A is this value is 10 to the power 17. So let's say this is our equation 1, this is our equation 2. So we put equation 1 multiplied with 10 to the power 17 and then minus equation 2. Is that okay for everyone? Okay, so what do we get here? This gives us 10 to the power 17. Okay, let me write precisely. This gives us, the first part is x0 plus 10 to the power 17 times x1 minus 10 to the power 17 minus the second part, equation 2, is x0 plus 2 times x1 minus 3. This should be equal to 0, right? That's why you calculate. And then what we say is that this is basically 10 to the power 17 minus 2 times x1 minus is equal to 10 to the power 17 minus 3. Is that clear to everyone in this room? Okay, so everything is so good. Now the question is, what is 10 to the power 17 minus 2? 10 to the power 17 minus 2 is 10 to the power 17. Well, you just said, well, but it's different. Yes, it's different mathematically, but they're the same in the floating-point representation. So because 10 to the power 17 is so far away from 2, as you explained earlier, when you take 2 out from 10 to the power 17, you take nothing out of it. It's still 10 to the power 17. Similar for 10 to the power 17 minus 3 is still 10 to the power 17. Of course, this number is made up to make sure that this works. So you ended up with the result in your equation that it's actually the same as 10 to the power 17 multiplied with x1 is 10 to the power 17. So your conclusion is that x1 is 1. Okay, so now you do this, you utilize this equation 2 to get the result that x1 is 1. Then you need to know x0. You put x1's value back to equation 1 because x1 is 1. So x0 will be 0, which is not correct. It's close to 0, but not 0. Okay. So what you can hope in this case is that you want to say that you want to calculate correct value and you do the exact calculation. If you don't do crazy stuff using floating points, you just look at this if mathematically. You have a times a x0 plus 1 x1 equals to 1 and x0 plus 2 times x1 equals to 1. You can directly do it, right? Now let me try to refresh this instead of putting the concrete number. Let's do this instead of 10 to the power 17. We do this a this is divided by a, the value of a, right? So now what you get, instead of getting this 10 to the power 17, you have this divided by a, and this is 1 divided by a. Okay? And then you cancel the x0. And what you get here is that instead of having this 10 to the power 7 minus 2, you would have this value over here is 1 divided by a. Right? And this is also 1 divided by a minus 3. And then you will get that x0 would be this value. Oh, sorry, x1 would be that value. Yeah? And then by putting that back, you will know that x0 is actually 1, not 0. Okay. So this gives you the nice illustration that, in fact, when a is close to 0, actually x0 is still close to 1, and x1 is also close to 1. Otherwise, you have something incorrectly done. Because otherwise, your x0 plus 2 times x1 would never be 3. It would be still 2, right? Any question for this? Okay. I hope I haven't given you too much complications so far. The question is that whether you really get a 0 or not, or whether your small number is small enough.
Aber hätten wir, nachdem wir herausgefunden haben, dass x1 1 ist, das Ganze in die zweite Gleichung eingesetzt, hätten wir das auch sofort für x0
Yeah, the question
auch
is why do you know you would use equation 2, not equation 1? Because according to the Gaussian elimination, you would only use the first equation, not the second equation. No, it's because I tell you it's wrong, so you try to find a solution. You run your algorithm, you will tell you another solution. Otherwise, you have to check again and again. Now, the question is that if you get contradictory results, which one is correct?
It's wrong. Just say it's wrong.
It's wrong. Okay. Any further question? If you want to do the scientific calculation, scientific computing, you need to understand the magic of floating points. Otherwise, you are doing something that you look at, oh, my system is not stable, but in fact it's stable. It's just wrong in your evaluation, in your floating point systems. Okay, so what are the problems? I told you the nice solutions, the nice problems we can have. There are problems that we should not try to solve. Those are difficult problems, like a cosine or tangent. You change a little bit in your value, and your number goes drastically up to something you cannot bound. So a small mistake you make will lead to a catastrophic mistake. Those are the systems that you should not use floating-point numbers at all. Those are the systems you also need to check whether your approximation using discretization would even work at all. Okay, so keep in mind that there are problems that we should not use floating points. So it's very dangerous if you utilize an unstable algorithm on a well-conditioned problem. It's also dangerous that you use a stable algorithm, the numerically stable algorithm, on a problem that you cannot have good conditions. For those two cases, you should not use floating points at all. Why can you use the floating points? First, you need to make sure that the problem has a well condition, that you can somehow make sure that a small mistake of your algorithm will not lead to a catastrophic mistake. This is so-called well conditioned. If your problem doesn't have such good conditions, you should not use floating points because we are losing our information in a small part. And if you have a well-conditioned problem and your algorithm is numerically stable, then you can use floating points.
Und was ist, wenn man einen instabilen Algorithmus auf ein schlecht konditioniertes Programm anwendet?
That's the one I try to skip. So let's skip the, yeah. There are problems that you cannot do any approximation at all. So this is, for example, the small disturbance of epsilon in tangent. So you make a small mistake here, and you have a big mistake in your result. It's a minor mistake in your x, but it's a big mistake in your f of x. So those are the problems that you should only say earlier, right? What are 14 points? We look at a nice statement at the beginning. 14-point numbers are like piles of sand. Every time you move them around, you lose a little sand and pick up a little dirt. The question is that for the back condition problems, when you lose a little bit sand, you will pick up a big amount of dirt. Your system is completely broken with a small loss of accuracy. These are the regions you should never use 14 points. Whether these are the regions you can use discrete values or not, it's also a question you need to answer. Usually not. Those are the problems that you need to have very precise calculation of that. You cannot tolerate any minor mistake. You need to make sure that the regions you look at is small enough that the error you accumulate is not going to lead to the catastrophic behavior. That's the first part. If your problem is not well conditioned, you should not consider that. Now, if your problem is well conditioned, but your algorithm itself is not well conditioned, then so your algorithm itself is not stable. For example, this one. This algorithm to calculate f of x is not stable because you lose too much when x is small. What are the alternatives you do? You first think about whether this would lead to catastrophic cancellation when x is small. You know that it would potentially not work, right? Because when we analyze that, you see some instability. What are the ways you get rid of that? You need to have a new algorithm. And the new algorithm should be numerically stable. And with that, you are able to deal with the problem. What is the algorithm that is numerically stable? You cannot use the hospital's algorithm, the hospital's rule, otherwise you cheat. You also can get the correct value of it. The algorithm you use in this case is tidal expansion. And with the tidal expansion, you are able to do it right. The tidal expansion for that problem is numerically stable. Okay, so this is what we want to say. Although you have learned the first part of the computer structures lecture that 14-point numbers are good to cover a wide range of numbers. You have to keep in mind that these numbers are not real. The worst one is that they actually potentially give you some problems in the range when you have to deal with the loss of accuracy in the mantissa. And with that, you have to keep in mind that there are algorithms not suitable for 14-point calculations. And there are also problems that you cannot even use 14 points at all. So before you apply 14 points to solve a problem, you should first ask yourself whether the problem should be solved using 14 points, and if yes, you should ask yourself again whether your algorithm can stably solve the problem. If your algorithm cannot stably solve the problem, are there alternatives or not? So, as Daniel suggested earlier, there are many ways to get rid of the 14 points. If you don't know the value of the range of your values, then you at least have to analyze which region your algorithm is stable. And if you are not forced to use floating points, don't use them. Use them with chaos. And of course, if you have chance to use fixed points, you should use fixed points. Floating points are nice to have, but it's more dangerous. And you need to analyze the suitable, whether floating points are suitable for your problem or not. With that, I conclude the first part of the lecture. We are not going to talk about representations anymore. We are also done with arithmetics. The next lecture will start with the optimization of circuits. Now we understand how to add, how to multiply. Now it's time to really look into the details of circuit design. So we are going to look at the structure optimization of circuits and also move on to deal with the flip-flops in the next weeks. So see you, today's Wednesday? See you next Monday.